Welcome to the world of Project AITHERION-SIGMA, a visionary leap in aerospace engineering. This platform reimagines how vehicles interact with their environment, blending plasma physics, electromagnetic fields, and AI harmonics into a unified system. Unlike traditional aircraft, which rely on mechanical thrust and isolated subsystems, AITHERION-SIGMA integrates propulsion, lift, cooling, and stability within a continuously interacting field ecology. The result is a craft that operates as a field-structured machine, where the electromagnetic environment is as crucial as the physical hull. This introduction sets the stage for a deep dive into the technical innovations, subsystem integration, and speculative science behind this advanced lenticular vehicle concept. The hull of AITHERION-SIGMA acts as a phased electromagnetic emitter, with thousands of synchronized emitters embedded in its skin. This distributed magnetic field lattice enables local magnetic shaping, plasma confinement, directional ion steering, and adaptive turbulence control. The electromagnetic environment is continuously altered, allowing the vehicle to respond instantly to changing flight conditions. The relationship is described by the equation $nabla times vec b equals mu 0 vec j plus mu 0 ver epsilon 0 frac partial. Vec e, partialité, highlighting the dynamic interplay between magnetic fields and electric currents. Plasma-intensive propulsion generates extreme thermal loads. To manage this, the vehicle incorporates liquid metal cooling loops, superconductive cryogenic chambers, radiative heat redistribution panels, and thermal phase reservoirs. The hull continuously redistributes thermal energy away from plasma-intensive zones governed by the relation $Q equals mc, delta T dollar. This ensures sustained operation and protects critical systems from overheating. AITHERION-SIGMA relies on autonomous AI coordination for plasma modulation, vector synchronization, field stabilization, and vortex timing. Human reflexes are too slow for these tasks. The distributed quantum AI architecture uses multiple synchronized nodes to control magnetic harmonics, plasma pulse timing, thermal balancing, and structural stress prediction. This enables near-instant adaptation to changing flight conditions and ensures optimal performance. The AI system constantly simulates future atmospheric states milliseconds ahead, allowing turbulence anticipation, obstacle prediction, field correction, and near-instant vector adaptation. This predictive modeling is essential for maintaining stability and safety during complex maneuvers, especially in turbulent or unpredictable environments. In Mode I, the vehicle uses vortex stabilization and plasma boundary control for standard atmospheric flight. This mode combines distributed lift, aerodynamic smoothing, and adaptive field management, enabling efficient cruising through various atmospheric layers. The integration of plasma and vortex systems ensures stable, responsive flight. Mode 2 activates a plasma compression sheath ahead of the craft, reducing shockwave intensity during hypersonic flight. This sheath acts as a dynamic buffer, minimizing turbulence and thermal stress, and enabling high-speed travel through dense atmospheric layers. The system's adaptability allows for rapid transitions between flight modes. In Mode 3, the craft absorbs atmospheric electrical energy while stabilizing itself through electromagnetic field balancing. This mode turns storms into operational environments, harvesting energy from lightning and charge differentials to recharge onboard systems and assist propulsion. The vehicle's resilience and adaptability are showcased in extreme weather conditions. Mode 4 enables the hull to transition into marine operation by increasing plasma cavitation around the lower hull. This adaptation allows the vehicle to operate seamlessly across air and water, distributing pressure evenly and maintaining stability in turbulent conditions. The lenticular geometry supports hover transitions and hydrodynamic plasma manipulation. Mode V speculates on electromagnetic force redistribution to reduce pilot stress during rapid maneuvering. This inertial dampening system uses distributed field control to mitigate acceleration forces, protect occupants, and enable high-speed, high-agility flight. The technology remains highly speculative, but represents a future direction for aerospace safety. AITHERION-SIGMA combines plausible near-future technologies, such as graphene composites, metamaterials, plasma aerodynamics, AI stabilization, superconductive power routing, and MHD experimentation with highly speculative concepts like inertial mitigation, gravity wave steering, compact fusion reactors, and large-scale quantum control. The platform is grounded in extrapolated scientific principles, but some elements remain theoretical and beyond current engineering capabilities. Project AITHERION-SIGMA represents a speculative but technically layered aerospace architecture. The system is designed around the idea that future vehicles may rely less on mechanical thrust and more on electromagnetic interaction, plasma fluid dynamics, adaptive materials, and AI-managed field harmonics. Rather than functioning like a traditional aircraft, the platform behaves as a dynamically stabilized field machine operating within a controlled plasma environment. Colonel James Hartman's conceptual framework introduces unique integration architecture and speculative engineering philosophy. The novelty lies in combining, scaling, synchronizing, and repurposing existing technologies into a unified lenticular aerospace system. Innovations include adaptive plasma envelope flight skin, Tri-Lobed vortex propulsion, Cobalt-Ion tug field system, fog particle vortex amplification, atmospheric charge harvesting, and more. Each concept transforms traditional aerospace approaches into dynamic, field-driven solutions. The adaptive plasma envelope flight skin, APFS, is a dynamically controlled plasma sheath, functioning as an aerodynamic boundary layer, thermal regulator, electromagnetic control surface, ionization medium, drag reduction layer, and partial radar scattering medium. Unlike traditional plasma systems, APFS treats plasma as a programmable atmospheric interface and energy recirculation medium, actively shaping flight control and maneuvering. The Tri-Lobed vortex propulsion architecture, TVPA, embeds a three-sector vortex control geometry inside the lenticular hull. Each lobe generates directional vortex circulation, manipulates pressure gradients, interacts with plasma ion flow, and redistributes thrust asymmetrically. The craft maneuvers by shifting circulating flow structures and modulating electromagnetic vortex coupling, functioning as a field-mediated fluid vehicle. The Cobalt-Ion tug field system, CITFS, uses ionized metallic particulates as temporary electromagnetic traction media. The craft releases cobalt-ion aerosols and charged particulates, which are manipulated by electromagnetic fields to pull, repel, anchor, and stabilize against ion clusters. This transforms ions from reaction mass into field-coupled environmental control structures. The fog particle vortex amplification system, FPVAS, releases engineered aerosols into vortex regions to amplify propulsion and steering effects. These aerosols act as active plasma interaction media, charged transport pathways, and vortex reinforcement structures, making the fog an integral part of the propulsion system. The atmospheric charge harvesting flight envelope, ACHFE, is designed to interact with storm electricity environments for energy recovery. Components include electrostatic perimeter collectors, lightning siphon channels, capacitive metamaterial storage arrays, and plasma discharge regulators. This system turns storms into energy reservoirs and propulsion assist mechanisms. The dynamic vacuum glide compression layer, DVGCL, forms localized low-pressure pockets ahead of the craft using plasma heating, vortex compression, and electromagnetic flow shaping. This approach attempts to reshape the pressure environment itself, moving the atmosphere around the vehicle rather than simply passing through it. The Quantum AI Flight Lattice, QAIFL, is an integrated distributed AI architecture controlling vortex, timing, plasma modulation, atmospheric sensing, field harmonics, stabilization, and predictive maneuvering. The vehicle behaves more like a dynamically adapting organism than a mechanically piloted aircraft, orchestrating all environmental interactions simultaneously. Plasma-Spun high-frequency gyroscopic stabilizers, PSHFGS, use electromagnetically rotating plasma rings as inertial stabilizers, attitude regulators, and harmonic dampers. This hybrid system replaces part of the mechanical inertia with magnetically constrained plasma circulation, enhancing stability and reducing moving parts. The Metamaterial Lenticular Hull Resonance Layer, MLHRL, comprises metamaterials, memory metals, conductive nanostructures, and thermal adaptive skins. The hull dynamically changes electromagnetic behavior, redistributes heat, alters radar interaction, and adapts resonant properties, functioning as an active system rather than a passive structure. The Multi-Environment Unified Lenticular Vehicle Theory, MUVT, envisions a craft capable of underwater operation, atmospheric flight, upper atmosphere, near space, and orbital maneuvering. Continuous environmental adaptability is achieved through changing field interactions, propulsion modes, and pressure management systems, rather than switching vehicle types. Distributed Field Line Steering Geometry, DFLSG, replaces discrete control surfaces with electromagnetic and plasma field asymmetry. The craft alters surrounding field geometry, redistributes pressure and plasma density, and steers through field gradients rather than rudders or ailerons. The Energy Recirculating Plasma Envelope Architecture, ERPEA, is designed for propulsion interaction, heat recovery, charge recycling, particle recapture, and ion reuse. This semi-closed energy ecosystem attempts partial energy recapture loops, reducing waste and enhancing efficiency. Electromagnetic Pressure Node Steering, EPNS, uses electromagnetic pressure asymmetry to steer atmospheric flow around the craft. Instead of redirecting engine exhaust, the system redistributes surrounding pressure fields, making the atmosphere a manipulatable steering medium. Harmonic Field Synchronization Flight Theory, HFSFT, synchronizes plasma oscillations, vortex timing, electromagnetic frequencies, and structural resonance into one harmonically controlled flight architecture. This cross-linked resonance management transforms flight into a harmonic synchronization problem rather than a purely mechanical one. The most important original idea of the AITHERION program is the philosophy that a lenticular aerospace vehicle can become an active environmental interaction system, not just a passive craft. This shift transforms propulsion, steering, thermal control, energy management, atmospheric interaction, stabilization, and survivability into one interconnected field architecture. The technical poster for Project AITHERION-SIGMA presents a multi-environment aerospace platform capable of atmospheric flight, high-altitude operation, orbital maneuvering, and theoretical transmedium transition. The design integrates exploded subsystem architecture, energy flow mapping, operational diagrams, plasma and electromagnetic field topology, structural layer analysis, mathematical annotations, and environmental deployment scenarios. The visual style resembles a classified aerospace engineering briefing. The lenticular disk geometry of AITHERION-SIGMA provides uniform stress distribution, symmetrical field propagation, distributed lift vector control, reduced aerodynamic discontinuities, high internal volume efficiency, omnidirectional maneuvering symmetry, and multi-axis stability. The disk profile is layered into concentric engineering rings, with a central luminous section representing the primary power and field control region. Subsystems are integrated into the hull, including plasma rails, stabilization gyroscopes, field emitters, sensor arrays, AI systems, and environmental shielding. Power is routed radially outward from the central energy core, supporting distributed propulsion, stabilization, and environmental interaction. Emergency backup systems ensure survivability and redundancy. The poster includes mathematical overlays symbolizing electromagnetic field divergence, plasma containment geometry, toroidal energy circulation, resonance harmonics, dynamic curvature relationships, and energy density calculations. Equations like $nabla C dot E equals rho varet psilon, $, phi equals oint B, C dot dA, $, and delta psi equals omega t plus phi, $0, provide a pseudo-engineering language supporting the scientific aesthetic. The concepts in Project AITHERION-SIGMA intersect with real aerospace research areas, including plasma aerodynamics, magnetohydrodynamics, adaptive metamaterials, hypersonic boundary layer control, distributed electric propulsion, AI-assisted flight control, superconducting systems, and advanced composite structures. These ideas could inspire research into plasma-assisted drag reduction, adaptive skins, electromagnetic stabilization, and high-speed maneuvering. Distinctive conceptual innovations attributed to Colonel James Hartman include plasma skin lenticular integration, vortex field propulsion layering, atmospheric charge harvesting, electromagnetic hull functionality, AI-controlled dynamic field synchronization, and multi-environment unified flight architecture. These innovations redefine aerospace vehicle design, emphasizing active environmental interaction and systems-level integration. Project AITHERION-SIGMA is best interpreted as a speculative advanced aerospace systems concept, integrating plasma physics, electromagnetic engineering, AI flight control, adaptive materials, science, distributed propulsion theory, and environmental energy interaction. While not currently realizable, it creatively combines real scientific disciplines into a coherent conceptual platform. Its greatest value lies in systems visualization, aerospace inspiration, conceptual integration, engineering imagination, educational presentation, and science fiction realism. The design communicates the idea of a future craft, where propulsion, structure, computation, sensing, and environmental interaction are deeply unified.